Last time we talked about this issue of goodness of fit, right? Which is a separate question than maximum likelihood estimation. So we have data, we have a model, and we call that M. We have a parameter. And so we're thinking about, we have a function f that goes from a space of possible parameters to some space of possible models. Maybe it's some real space. So given a parameter, which might be a vector, like a set of probabilities, for example, it defines a model that corresponds to theta that is a probability distribution that's given by the parameters. Right? So, for example, for a binomial distribution, theta is just the number p. For a multinomial distribution, theta is a vector. And we could have some other example like that sort of shows what's going on, where suppose I have a multinomial distribution where I have a vector of probabilities, but that vector is restricted and depends on a smaller number of variables. So like, maybe it's theta squared, or something like that, right? And then I have to divide by 2 theta plus 2 theta squared. Right, so up to normalizing by, let's multiply, 1 over 2 theta plus 2 theta squared. Okay. So in this example, each probability in the multinomial distribution is some number, and it depends on some single parameter theta. So this would be the model, and it's an image of this. Okay. So there's different questions we can ask. So given the data, the probability distribution that we get out, which lives over here, defines a notion of maximum likelihood. And we can use either an explicit closed form solution or an algorithm to figure out what the best theta is, the maximum likelihood theta. And that is in some sense an answer, right? But then we're interested in other questions, like we talked about if you think of theta as a random variable that depends on the data, if the parameter is a random variable or the vector of parameters, then we're interested in the asymptotic distribution of this, right? It's how this estimate gets spread out among possible estimates, and if it's normal, we can create, confidence intervals, and we can do hypothesis tests. And then there's in a sense, completely separate question, which is, once you've done all that, you've found the theta that best explains the data, which corresponds to your model, can you separately judge whether that model was a good model to choose or not, right? So I could find the theta which best fits, but then I might decide that this is a terrible model, right? And that's almost a completely separate question, although it's related, and so what we'll talk about today is that. So as a hypothesis test, what are we saying? We're saying the null hypothesis is that the model, maybe M0, the null model fits versus the alternative hypothesis, a model that we're assuming the null hypothesis model does not fit. And so we need to construct a statistic that measures this difference. Okay, so you can think about this as a multi-step process. Step 1, estimate the parameters. solve our maximum likelihood equation, run our iterative algorithm, decide what we think the parameters are. Calculate probabilities. If we're thinking about if we're thinking about our discrete model for a table, we have to compute the cell frequencies. So for example, we would take this, if we estimated theta, and we got some vector theta hat, theta squared, and then we divided it all by this constant to make them sum to 1. And then we'd have to multiply them all by the sample size, and then we'd get our expected counts. Right? And we can't avoid doing this because, in the space of proportions, right, we have our data proportion, or our empirical distribution, p hat, and then we have the model, and we have the p theta hat, the best distribution, the best fit distribution, and we're trying to estimate sort of this distance, right? We're trying to decide whether or not we're close enough to the model to say we live on it, and the statistics that tell us about whether this distance is significant or not, of course, has to depend on the sample size. So it's not enough to estimate the probabilities, we also have to estimate the frequencies. So step 3, calculate the distance here, and we're going to have 2 ways of measuring that distance. And 4, decide if distance is big enough to reject the null. Okay. So we have 2 main tests. Or ways to measure the distance between a model and the data, and they're called the Pearson, which you may also have heard called the chi-squared test, and it's called the deviance. And they both have a chi-squared distribution, but they're calculated in a different way. So before I say what they are, if you look at this picture, how would you think to measure the distance between the data and the model? Give me an idea for measuring that distance.
The distance formula?
That's a very good idea. That's this idea. Okay? But we have to correct it a little bit. Okay, so if we take that idea, which is, all right, just what's the Euclidean distance between this and that? The Euclidean distance would be square root of, p hat minus p theta squared. Sum I equals 1 to number of cells, pi hat minus pi of the model, square that, right? That would be the Euclidean distance. It turns out that that doesn't quite work. One of the reasons it doesn't work is because, for example, it doesn't include the sample size. So we have to figure out a way to adjust that idea to include the sample size, and the statistic, the chi-squared or Pearson statistic, looks like this. We sum j equals 1 to k, xj minus n pi j hat squared. So this is for a table of counts with vector, estimated vector pi j. So pi j is what I wrote as p theta. So this is what we estimate from data on the model. And this is just what the data is, the raw data. Okay? So it's almost a distance formula because of this part, right? It's the, and adjusted for the sample size, so it's the count that I actually observed in that cell minus the count that I expected given my fitted model. So my fitted proportion, I multiply by the sample size, I get a fitted model. Take the difference of those two things, I square it, so that looks like a distance, like a Euclidean distance, and I sum it up. But it turns out that to get the statistics to work out, I need to weight this sum. So I don't just use the Euclidean metric. You can think about it as using a, if you know about this sort of thing, instead of using a sort of the straightforward metric, I kind of do a change of coordinates, linear chain of coordinates, or I change the metric. And so what I'm doing is I'm weighting it by this quantity, n pi hat, so the expected quantity. Okay, dividing it by that. So in other words, instead of taking the absolute difference, we're taking the relative difference, right? The relative distance, and the proportion. You know, how far off am I? As sort of more like a percentage than a thing. Okay. So another way of saying that is that this is the sum of the observed count minus the expected count divided by the expected count squared by the expected count. Okay, so it's a scaled Euclidean distance. And so, you know, if we have some example, like we had an outcome over here, and it was, I don't know, 5, 6, 2, 1. And so I have 11, 14 is n. And then I multiply 14. So for these cells, I get like 14 times theta divided by the constant z equals 2 theta plus 2 theta squared. 14 times theta over z. 14 times theta squared over z. 14 times theta squared over z. So these would be my observed, and these would be my expected. Okay. And what I'm doing is comparing these numbers as how much does the squared difference of these exceed, how much greater is it than E. Okay, so that's the statistic. And then the other approach, can I think of another way of measuring this distance? Something that, so Euclidean distance is a little bit weird, right? Because it doesn't really have anything to do with probability. Let me put it this way. If I just tell you this model, M, and I tell you a point, a proportion, and I don't tell you anything about the sample size. So I just tell you, okay, here's the set of all probability distributions that lie in the model. Here's what I observed, the empirical distribution that I observed. Which distribution on this should I choose as the best representative? It's not the Euclidean distance closest, right? We already know how we select this P. What's the principle for selecting theta?
Like finding the best model.
Right, but what do we mean by the best model?
So you're wanting us to find the maximum.
The maximum likelihood, right. So we want to pick the P that is the theta that makes this thing most likely, makes the data most likely, right? So it turns out that there's actually a thing which is like distance that does that. It's not Euclidean distance, it's something else. Okay? This thing is called KL divergence. So the KL divergence between two probability distributions, d KL PQ, is just the sum over, so I equals 1 to k. Think about there being k cells, or k possible outcomes, pi log pi divided by qi. Okay? So it turns out that minimizing this distance between the observed and the expected, or between the model. So I let, let's see, I want Q to vary, I think. So I could be mixing this up, but let's say we minimize over Q, dKL, PQ. And the other problem of maximizing likelihood, maximize over Q, L, X, so this is the empirical, Q. Turns out these are the same problem. So you can do a little calculus if you want, and take some derivatives and convince yourself that that's true. But so what this is telling you is there is a notion of distance, something like distance. It's not strictly a distance because it doesn't have all the properties of a metric, but it's like a distance, which minimizing that distance is the same as maximizing likelihood. Okay, so that's the second idea for measuring the distance. Instead of using this Euclidean distance, we should use this distance that knows about probability theory, this likelihood type distance, KL divergence. And that, if you work out the details, leads to this deviance or G squared statistic. So it leads to, that's G squared equals 2 sum j equals 1 to k xj log xj divided by n pi hat j. So that's the fitted one. And this comes from, so this G squared is proportional to the KL divergence of empirical to theoretical. At the best fit. Okay, that's the idea. So I'm skipping over a lot of details, but I'm just trying to give you an intuition of what's going on. Okay, so these are the two main ways we can measure distance, just literal Euclidean distance, and the other notion of distance, which was the one we were implicitly using when we were doing maximum likelihood estimation.
What does it say under n pi hat j?
Good question. It says, I have bad handwriting. Fitted. Okay. Okay, so other ways of writing this that are possibly instructive is 2 log L of px divided by L of pi hat x. So this is empirical and this is null, or null and empirical. And I can also think about it as so it's sometimes called a likelihood ratio test statistic because you can express it in terms of likelihood ratios. And in terms of observed and expected, I could write it as 2 sum over j oj log oj over ej, observed over expected. Okay. Okay, so these are both functions. This first, the Pearson one, is sometimes written x squared or chi-squared of x, and the vector of probabilities, and g squared is also a function of the outcomes and the probabilities. Okay, so these things measure how closely the model fits the data. They measure this distance. Now, what can we say about them? Well, okay, so if we just set these things to be exactly equal to the proportions we observed, then both statistics are 0. Right? So if we're in a situation where this thing actually fills up the whole space, and I can always pick a model that exactly matches it, of course, then the distance is 0, no matter how I measure the distance. If not, then both this Pearson and g squared are positive. And if they're big, the agreement with the data is poor. So just like any other type of statistic or hypothesis test, the strategy that we want to use is to, now that we've figured out a measure of distance, we say, okay, assuming a null hypothesis, like that we're on the model, and we generate data from some point on the model, right? So suppose this is the true probability distribution, and we just draw from it. Of course, we're not going to get exactly a point on the model. I mean, even because of just rounding errors, right? So if I have, I have some vector of probability distributions, I don't know, E, 1 over E, 1 over E, 1 minus 2 over E. There's no way I'm going to get integer values that work out to be exactly that, right? So of course, there's no way I'm going to land, in general, when I draw from this, I'm not going to land on the model. Okay. So what I want to do is think, okay, I start with something on the model, I draw from the distribution, and now I want to compute the distribution of distances. So what is the distribution of this, and what is the distribution of this? The distance statistic, given that the null hypothesis is true, right? That's how I do my hypothesis test. All hypothesis tests have that form, right? I assume something about the data generating process, I compute the value of a statistic, and I ask myself, am I farther away from what I would expect than I would have expected from my chance? Right? Okay, so that means that in order to use these things to do hypothesis tests, we just need to know what their sampling distributions are. And as I'm sure you could guess, given the names, and of course this has to be true for large n, because for small n everything goes wrong. It's the chi-squared distribution with the degrees of freedom k minus 1. And this number is going to change. Okay. So this number, well, I'll explain maybe towards the end of today, but you should think about this number as counting not, well, it's the free degrees. It's kind of like if I have a small model inside a big space, it counts how many dimensions are missing. Right? So if I have a one-dimensional point inside a 10-dimensional space, it's 9. Or one-dimensional line inside a 10-dimensional space is 9. If I have a 2-dimensional space inside a 3-dimensional space, this will be 1. Okay, so this counts kind of the number of ways that the directions that I can go to fail, the directions that I can go away from the model. Okay, it's called the codimension in geometry. Okay. All right, so then we want to do a hypothesis test. Our hypothesis test should say reject the null hypothesis that we were on the model, that our data was generated by a point on the model, that our data was generated by this, if the chi-squared Pearson statistic or this g-squared deviance statistic exceeds the threshold. The chi-squared distribution with k minus 1 degrees of freedom, or more generally the codimension degrees of freedom applied to my threshold for significance. So I want to take if chi-squared looks like that, it's the usual strategy, right? So this is the distribution of expected distances. Assuming the null hypothesis, I pick my significance level, 0.05 or whatever, and I say, am I past this significance level? Okay. Did my calculated chi-squared or Pearson or g-squared statistic exceed? Is it more? It's the usual strategy, right? Okay. And then there's functions, of course, in the software for doing this. I'm not doing any computer demos today. All right, so questions about that, what we've said so far, the strategy for measuring goodness of fit.
I have a question about the degree of freedom. Like for example, like we have like 3 parameters that we estimate, and they both add to like 1, right? So we just need to estimate like 2, and we would automatically get the third one. That's kind of like k equals to 3 or k.
Yeah, so think of it like, so say I have the dice example. You know, there's, I have 6 outcomes. There's sort of 5 degrees of freedom. And suppose I have, say, a 2-parameter family. Then I want 3 as my chi-squared degrees of freedom, which is 5 minus 2. We'll talk about that more in a bit. Yeah. Okay, so some comments. So this counts the directions, how many directions there are that you can go wrong. Right? So the dimension of the space of errors. Okay. Of course, when n is large and the model is true, that's when the theory works. The approximation is good. So it's not a normal approximation here, it's a chi-squared approximation. The approximation is good. And the Pearson test and deviance test should agree. So if I go to the limit of large n at this, then these 2 things will converge. Both converge to the appropriate chi-squared distribution. We have, of course, rules of thumb about what large is. So an old rule of thumb is if n is big enough so that all the expected cells are at least 5, the approximation is okay. Okay, so that says, okay, infinity is 5 or more. And when that's not okay, you can sometimes go to an exact test. So later on we'll talk about how to do exact tests. So when these don't agree, or when you don't believe that you're in the asymptotic regime, there's other things you can do. You can just enumerate all possible outcomes, basically. Another rule of thumb that's a little bit more recent is, let's say, less than 20% of cells have this EJ n pi less than 5. None below 1, then it's okay. So, I mean, these are sort of terrible like rules of thumb. I mean, there's some amount of theory that goes with it, but sometimes it's just people have done this a lot and come up with some experience. I'm not crazy about making decisions that way, but sometimes that's what we have to do. Of course, just as with what we were talking about earlier in the week, we can use the agreement of these things. Just as we can use the agreement of walled likelihood ratio and score tests as a measure of proximity to infinity, we can use the agreement of these as a way to sort of diagnose. Right? Can be diagnostic. In other words, if the Pearson and the G squared are very far from each other, maybe we should watch out. And if they're close, maybe we're okay. Right. And what do we do if we fail the rule of thumb, and these are far apart, what do you think we should do? We have some big table with lots of different possibilities. Big contingency table. Many cells less than 5. So you did a study, you asked too many questions. Yeah.
So I would collapse.
Yeah.
But I actually have a question.
Yeah.
So if your chi-squared and your g-squared disagree, is the only result you get from that n is too small? Like, what are you concluding by their disagreement?
What am I concluding? It's just a hint. So the theory tells us that if the model is true, as n goes to infinity, these will be close. These will both converge to chi-squared, and they'll be very similar, right? So it's not, so if that doesn't happen, if they're not close, one of these assumptions had to fail. The model is not true,
Okay.
or n is not large enough.
I mean, I'm just thinking about the case that n is large, then I still disagree.
Well, whether n is large or not very much depends on the specific distribution you have, right? So like in the binomial case, if we're close to 0, so like in the binomial case, it's kind of like if np goes to a constant, then n is large enough. But if np goes to 0, then n is never big enough. So it depends on how this is changing with your sample size, if it's changing. So whether n is large enough is sort of more of a statistical question than whether it's big for humans. And I guess we'll talk later on about ways to study that explicitly in terms of power and things like that. Okay. So right. So your answer to the question was right, in that what do we do when it has a big contingency table and everything's telling we collapse, right? But of course, we have to watch out for chihuahuas. Right? So we have to watch out for if you remember my example from the first week. If you don't remember, then so you have to watch out for Simpson's paradox and other issues. Okay, so you have to be careful that collapsing the cells doesn't change the associations. Okay, which of course is a brutal question, because when the cells are so small, it's also hard statistically to answer those questions, whether it's okay to collapse them. So it's a delicate thing, and you probably want to do several different techniques and try to see that they all give similar answers. So the other things you can do is you can do the same sort of ad hoc stuff, like add 1 to all cells. Seems crazy, but sometimes it actually works. Or add a small value to all cells. Or we could do other things, like maybe change our inference technique to something else. And the other thing we can do is exact inference, which we'll talk about a little bit more later in the course. That is, we abandon the normal approximation, abandon the chi-squared approximation, and just try to directly compute the probabilities, which is computationally intensive, but computers are fast, so that's okay. And the one other thing I want to note is that okay, so if the data, if the deviance or the Pearson statistic are really small, right? Some chi-squared, I went way over here. That can be suspicious. That can suggest that there's something, that the data may have been fabricated, right? Or may have been sort of gently averaged toward the hypothesis that you wanted to do. And somewhat famously, people now think that Mendel's genetic experiments were too close to theory, and that they were so close to theory that they were that he probably fudged the data to make it match. And the way that you can calculate that is by computing these statistics and then seeing that, hey, that's too good to be true. You know for sure it could have been, but in a statistical sense, too good to be true. Okay, so now I'm going to do a couple of numerical examples, just to sort of make these concrete. And these again are these numerical example is in the notes. So just listen. Okay, so dice. This is a dice experiment. I roll a 6-sided die 30 times. They're cells. They're labeled 1, 2, 3, 4, 5, 6. Is this an ordinal or nominal variable? What do you think? Yeah, it's a nominal masquerading as an ordinal. There's numbers, but the numbers don't really mean anything, right? Okay, so this is our table, and I'm going to add 3 more columns to this in a little while, so leave a little space. You're writing it down or in your mind. Okay, so let's think about our, instead of this picture, where we have a model that has a parameter and we have data up here, let's think of a really simple one, which is that the model is just a single point. That is, our null hypothesis is that the die is fair. And we'd like to test that null hypothesis. That is, we're saying the distribution of rolls, this variable x that we've been measuring, is multinomial with 30 draws and parameter vector all 1/6. Okay, so that's our assumed model, and so we want to measure the distance. So we compute the expected counts. The expected counts is that each cell is just 5. Right? We expect that we get a 1. We roll a 1 5 times. We roll a 2 5 times. We roll a 3 5 times, and so on. So under the null, that's what we think. And then we can compute our goodness of fit statistics. Okay, so all we do is add up observed. So 3 minus 5, 3 minus 5 squared divided by 5. All the expecteds are going to be 5. So I'm going to put 1 5 out in front. So we have 3 minus 5 divided by 5 corresponding to or 3 minus 5 squared divided by 5 plus 7 minus 5 squared divided by 5 plus 5 minus 5 squared divided by 5 plus 10 minus 5 squared divided by 5 plus 2 minus 5 squared divided by 5 plus 3 minus 5 squared divided by 5. And that's 9.2. Okay? So our Pearson chi-squared statistic is 9.2. That's our measure of the distance between the null hypothesis and the observation from the point of view of the null hypothesis. Right? And I can compute, similarly, the deviance statistic. And that's twice. And then I have to take logs, 3 log 3/5 plus 7 log 7/5 plus 5 log 3/5 plus 10 log, that's 5 log 5/5 plus 10 log 10/5 plus 2 log 2/5 plus 3 log 3/5. That's 8.8. Okay, great. So they're sort of close, but not equal. And remember that we're comparing them against the same asymptotic distribution. We expect them to be close if n is reasonably big, which it sort of is here. There's some cells that are below 5, but okay. And then we have to compare it against the probability that a chi-squared variable with 5 degrees of freedom is greater than or equal to 9.2, and that's just 0.1. And the probability that a chi-squared variable is greater than or equal to 8.8 is more than that, is 0.12. And here 5 is secretly 5 minus 0, right? Because the saturated model is 5-dimensional, because I have 5 free variables, and then the 6th one is fixed, 1 minus the rest. And I'm subtracting from that the dimension of my model, which is just 0. It's only 1 point, so it's 0-dimensional. So that's what 5 is here. It's the number of directions that I can go wrong. Okay, so those aren't very significant p-values. So this says you can't reject the null. Okay, so this is from doing this experiment based on this sort of hypothesis test. We can't tell, it doesn't provide evidence that the die is not fair. Okay. So let's do another example, which is this Mendel type example. So we have some tomato plants, and they have a phenotype. So they have, let's see, we have cut leaf tomatoes and dwarf potato leaf tomatoes, and we have 11 of them. 926, 288, 293, 104, 1611. And this is, let's say, T, C, T, P, D, C, D, P. Okay, and from genetic theory, we think that the ratio of phenotypes should be 9 to 3 to 3 to 1. And we'd like to know whether the data we saw matches up with that theory, that hypothesis. Okay, so again, this is a zero-dimensional null hypothesis, right? Our null hypothesis is not a whole model, it's just one set of ratios. We're totally fixed binomial distribution. And so our vector of probabilities in the null is 9 over 16, 3 over 16, 3 over 16, 1 over 16. And we have expected frequencies which are 906, 302. Well, let's get them there. These are not going to be integers generally. 302.1 and 100.7. And you can compute the Pearson and deviance statistic and get that the Pearson statistic is only 1.47, the deviance 1.48. So in this example, you can tell that, both because, well, hey, this is a pretty big number, and because these are really, really close, well, these things suggest that n is close to infinity, that the asymptotic regime has taken over. I'm going to leave this up because I want to add a column to it. And what's our chi-squared distribution? How many degrees of freedom? 3. And so the p-value probability that this is greater than or equal to 1.48 is 0.69. Okay, so we really violently failed to reject the null in this. Okay? The data fits really, really well. Or maybe even too well. Okay. Okay, questions?
So I know that the dimension of the model is the 9331 is 0-dimensional. Where does the 3 come from? Just there's 4 things and one is
Yep.
kind of the other.
Well, because so remember, this number is the difference between the saturated model, like the model which could model any ratio, which in this case is 3-dimensional. There are 4 outcomes. So the space of probability distributions on 4 outcomes is 3-dimensional. It's a tetrahedron, right? And it's 3-dimensional, and so it's 3 minus 0. Okay, so the next thing I want to talk about is residuals. So that's what these extra columns are for. Okay, that is, okay, the G and the Pearson statistic gives you a summary, right? They tell you one number which measures that whole distance. Of course, that is a summary of the deviance from the model in all possible directions, all of the degrees of freedom possible directions. The other thing we can do is we can look at how much each data point or each cell is contributing to that. Each dimension is contributing to that, and that helps us do some diagnostics, right? So just like in regression, you look at the residuals and you ask yourself, you know, is this evidence that my assumptions are bad somehow? That, you know, that I can do a transformation, or I should think about my problem differently. Same way here, we want to look at the residuals to make decisions like that, get clues about the data. Okay, so the residuals are fairly straightforward, so we express both of these statistics, these distance statistics, as sums. And so to get the residuals, we just break the sums apart into their components. So the Pearson is a sum j equals 1 to k of some quantity, where this is just observed minus expected divided by expected squared. The cell count minus the expected cell count under the model squared divided by the expected cell count under the model. Okay, so in a totally trivial way, it breaks up into the contribution from each cell. And if I take the square root of this, well, not the square root, but the right square root. There's 2 square roots. And obviously I want the one whose sign agrees with the direction of the error. And then this is the residual. This is the Pearson residual for cell J. So it tells you, is this cell above or below, you know, what's expected from the count. So do I want to write these yet? Okay, why not? Okay, so observed, expected, all the expected values are equal. Observed minus expected divided by the square root of expected gives me these residuals. First I'll do this Pearson R residual. This is minus 0.89. This is plus 0.89. This is 0. This is 2.24 minus 1.34 and 0.89. Okay, so the only one, you know, as you of course you can read from the table, that's kind of big is that one. Right? And that's kind of a rule of thumb. So the rule of thumb not for significance, but to look more closely is this kind of two times. So this one's a little bit big. And so that's one thing to, it doesn't seem to fit very well for that cell, but of course we know that overall there's no significance. So it's not very strong evidence, but that's a good, yeah. Twice, implicitly, twice the square root of the expected. Yeah. Okay, so we can all do the same thing for G, for the deviance. So we can think of G as the sum of some other residual epsilon. So we're going to add another column. So these are the R's. These are the epsilons. And epsilon is square root of 2xj. So this one we have to be a little bit more careful. Xj divided by n pi hat j. We're taking the absolute value of that, and then we're multiplying that by the sign of observed minus expected. Because we want it to be in the correct direction. But okay. So we can fill those numbers in. This one is minus 1.75, 2.17, 0, 3.72, minus 1.9, 1 minus 1.75. Okay. So, also this one flags this, and it also sort of flags that weakly, but that's pretty close to 2. So. And this flagging of residuals is at this point not a formal thing. It's just saying, maybe look more closely at that part of the data. Yeah.
So the inside of that equation is multiplied by the sign, or the outside?
The whole thing. Anyway, this calculates the size of the residual. We just want to make sure it goes in the right direction. Yeah.
The rule of thumb. So are you comparing the 3.72 to 2? Which number are you comparing?
I think I want to compare it to 2.
And how did you get 2? Or that's the rule for all?
Yeah, so let me think about this for a second.
I think from the note it says k minus 1.
Yeah, that's better, right? Okay, that's exactly. So the notes are saying Rj versus square root of k minus 1 over k. Yeah, is it twice that number? Because this is kind of this is equal to the mean. The expected deviation, so expectation of a chi-squared with k degrees of freedom, k minus 1 degrees of freedom is just k minus 1. So we're saying, okay, the expected value of chi-squared is k minus 1, and then to scale that to the residual contribution, we should divide it by k and then take the square root. So this is the expected value of each residual. And then we're saying compare it to that. And if you look, so if you look in Agresti, or maybe we'll talk about it more as the course goes on, of course you can change this to a completely formal statistical test where we say, is this residual significantly different from 0? The problem is that, of course, to do that, we have to do kind of a multiple hypothesis testing thing, right? So we're not testing one thing, we're saying, is any of these big? And it should be a more stringent requirement than any one. Just like, if I do a coin flipping experiment or something 100 times, how many times do I expect to do something which is significant at the 0.05 level, different from fair, well, 5 times, right? So just like similarly here, you have to do you can do a significance test. Is the residual big? And you do a correction for how many cells there are.
So universally, we're comparing the residuals to 2.
No, stick with that. We're comparing it with that. For the g squared, is it the same number? I don't know. I have to think about that. Yeah. You're comparing it to this number. Yeah, I guess it's both this, but well. No. So in this case, what is that? That's
6.
yeah, because this is close to 1 here, right? Yeah, because this is 2/3, the square root of 2/3. So it's close to 1, so twice that is, yeah. So that's what's going on here, why it's 2. But you're right, it should be twice this number here, being a flag. Yeah. Good question, thank you. Okay, so the last sort of thing I want to talk about with respect to this stuff is more about 0 cells. So of course, 0 cells cause problems of all sorts. So this one can be calculated, no problem. If you use the wrong formula for g squared, you'll get an error, you'll get a division by 0. But you can rephrase it, so you can rewrite this g squared in a way that doesn't divide by 0, which is like this. G squared equals 2 log product j equals 1 to k xj over n over pi j to the xj. And then when you say 0 to the 0 is 1, and then it doesn't cause a problem. But more seriously, if this vector pi has zeros, like the null hypothesis, then the chi-squared approximation breaks down. I guess pi hat, I mean. So again, we have the same strategies for dealing with that, which is that we can add small amounts to each cell. We can collapse cells, we can remove cells, do that, do the usual, or redo everything in a different inference framework, like Bayesian, that deals better with zeros, with small sample sizes. Okay, and then there's just one distinction that we want to make between different types of zeros. So those were implicitly what I was talking about there, sampling zeros. So you've done the experiment, you've asked lots of questions, some of the cells just happen to be 0. And the other kind you can get are structural zeros, which is that for theoretical reasons, physical reasons, whatever, some cells must be 0. In other words, some cells represent things that are impossible. Okay. So there are techniques that can deal with both sampling zeros and structural zeros, I would characterize them as more advanced, and we'll talk about them later in the class, or you can do them in your project, or you can deal with it if it comes up. And there's still sort of research happening in these areas. One of the things that's definitely going to happen with structural zeros is that it's going to change our degrees of freedom, right? It's sort of obvious, right? So like if I have a die and it doesn't have a 6 face, right? It has 2 5s or something, and the 6 is impossible to roll, I've lost 1 degree of freedom. Right? Just one. So this will generally mean you'll get a smaller degrees of freedom. That's one of the things where we subtract degree of freedom for each structural zero. And there are some other strategies that we can use to address the situation. But they're sort of subtle. Okay. Okay, so the last section in the online notes is just, it doesn't add anything to it. It's the way I've been setting it up all along, which is that you think about your vector as being a function of some smaller number of parameters. In that case, as I said, you just, the degrees of freedom are equal to the difference between the ambient degrees of freedom, the degrees of freedom in the saturated model, or in a model which can represent all possible probability distributions, and the model that you're using. Okay. So one of the things that I work on in research is algebraic geometry, it's something called algebraic statistics. And one of the problems that is very common in algebraic statistics is that when this model is complicated, a complicated function of the parameters, it's actually quite difficult to compute the dimensions. Sometimes that's like a research problem, or they're unknown, or whatever. And there's some, I taught a class last semester, a lot of which was about how do you compute the dimension of this thing, the image of this thing. Because what matters actually is not the number of parameters, but the image of the number of parameters. So if I lose parameters if I have redundant parameters here, then I need the degrees of freedom which are equal to the, say I have 10 parameters, but it only creates a two-dimensional image. It's the 2 that I want to use, not the 10. And so figuring out whether there's redundancy and all that is quite difficult. But in the models that we'll encounter in this class, that should never happen. It should always be just one-to-one from parameter space to the space of probability distributions.